In this video, we will define the determinant of a square matrix. To each square matrix A, we will associate a number, det A, which is called the determinant of the matrix A. So often we'll also denote the determinant of a matrix by writing its entries between vertical bars instead of parentheses. So this notation here denotes the determinant of this matrix here. The definition of the determinant that we are going to give will be inductive. What this means is that to be able to determine the determinant of an n times n matrix, we will need to be able to compute determinants of n-1 times n-1 matrices. And to compute these, we will need to be able to compute determinants of n-2 times n-2 matrices, and so on. So let's begin with determinants of 1 by 1 matrices. So given a 1 by 1 matrix A with entry A, then we define the determinant of A to be equal to A. Okay. Now let's suppose we have an n times n matrix A with entries A, I, and J. And let's suppose that n is greater or equal to 2. Then we define the ij minor, mi and j of this matrix to be the determinant of the matrix obtained from A if we delete its ith row and jth column. So let's see an example. So suppose A is this matrix here. Now M11 is going to be the determinant of the matrix obtained from A if we delete the first row and the first column. Now this is a 1 by 1 matrix with entry 1. So M11 is equal to 1. What about M12? We need to delete the first row, second column. So we are left with this entry here. So M12 is minus 1. M21, we delete second row, first column, so M21 is 2, and M22, we delete second row, second column, so M22 is equal to 3. And if we have, for example, this 3 by 3 matrix B, and we want to obtain M23, that means that we need to delete the second row, third column, and what we get is the determinant of this matrix here. Of course, we don't know yet how to compute it, but we'll soon see how we can. Okay, so far we've defined the ij minor, and then the ij cofactor, Cij of A, is defined to be minus 1 to the I plus j times mij. So the cofactor is either plus mij or minus mij. So for example, C11 is going to be M11, because 1 plus 1 is 2 and minus 1 squared is equal to 1, while C12 is going to be minus M12 because minus 1 to the 1 plus 2 is equal to minus 1, etc. So a convenient way to determine whether Cij is equal to plus Mij or minus Mij is to look at the following metrics. So for example, if I look at C12, this is the 1, 2 position, so I need to put a minus. If I look for C33, it's 1, 2, 3, 1, 2, 3. I look at this position, so I need a plus. Okay, so now we can write down the definition of the determinant. Suppose we have an n by n matrix A with entries A, I, and J, and with cofactors Cij. Then the determinant is defined to be the sum from j equals 1 up to n of A, I, and J, Cij. So what this means is that we multiply the elements of the first row of A, and we multiply each element with the corresponding cofactor, and then we add all this up. So let's take an example. So we start with this matrix A, and we want to compute. We compute C11, delete first row, first column, so C11 is 1. And for C12, we delete first row, second column. M12 is minus 2, so C12 is minus 2, which is 2. And then the determinant of A is A11, which is 3, times C11, which we found out is 1, plus A12, which is 5, times C12, which we computed to be equal to 2. So the determinant of A is 13. And in general, the determinant of the matrix with entries A, B, C, and D is A11, which is A, times C11, and we obtain C11 by deleting first row, first column, we have D. So far we have A times D. And then we need to compute A12 times C12. A12 is B. C12 is minus the minor, which is M12. And M12 we delete first row, second column. So M12 is C. C12 is minus C. So A12, C12 is minus B times C. So the final answer is A times D minus B times C. And the way to remember it is this times this in the main diagonal minus this times this. Okay, so let's see a 3x3 example. Suppose we have this matrix A, and we want to compute the determinant of A. This is equal to 5 times C11, where C11 is equal to M11, which is obtained by deleting first row, first column. So it is the determinant of this matrix here, minus 3, 1, 1, minus 2. Then we have plus A12, which is 1, times C12. And C12 is equal to minus M12, where M12 is obtained by deleting this row, this column. So it's a determinant of this matrix, 0, 1, 4, minus 2. So it's minus 1 times the determinant of 0, 1, 4, minus 2. And the minus here is, we have the minus here because we need to write down C12. And the determinant here is M12, which is minus C12. And finally, we have minus 2 times the determinant of the matrix obtained if we delete this column, this row, which is 0, 3, 4, 1. And now we need to compute these three 2x2 determinants. And we know how to do it. For this one is 3 times 2, which is 6, minus 1 times 1, which is 5. For this one is 0, minus 4. For this one is 0, minus 12, so it's plus 12. We sum all these products up, and we get the final answer, which in this case is 5. Now, the definition we have given of the determinant is known as the cofactor expansion along the first row. And in fact, it turns out that taking cofactor expansion along any row or any column, the answer we obtain is also going to be equal to the determinant. So for example, what this means is that the determinant of A is also equal to the sum from j equals 1 up to n of Aij, Cij for any I. This is the cofactor expansion along the ith row. When I was equal to 1, it was the cofactor expansion along the first row. But if instead of looking at the first row, we look at the second row, then again, the determinant is going to be equal to this cofactor expansion. And also, it's equal to the sum from I equals 1 to n of Aij, Cij for any particular j. So this is cofactor expansion along the jth column. So if we want to compute a determinant, we can take cofactor expansion along any row or any column that we wish. And we can use this fact to compute determinants quicker. So let's see an example, and let's take the matrix of the previous example. Now, instead of taking cofactor expansion along the first row, we'll take cofactor expansion along the first column. So the first thing will multiply 5 with the determinant obtained if we delete the row, the column, and row containing 5. So it's 5 times the determinant of minus 3, 1, 1, minus 2. Then the next entry is 0, and this is going to be multiplied with the determinant obtained if we delete the column and row containing 0, which is 1, minus 2, 1, minus 2. Of course, we'll actually need a minus here because we don't multiply with the minor, which is the determinant. We multiply with the cofactor, which in this case is minus the determinant. Of course, here it doesn't matter because whether it's plus or minus, the answer is still going to be 0. And the final one, we multiply 4 with the determinant obtained if we delete this column and this row. So it's with the determinant minus 1, minus 2, minus 3, 1. Now what is this determinant? Is 6 minus 1, it's 5. So we have 5 times 5. We have 0 from here. And from here we have 1 minus 3 times minus 2, which is 6. So it's 4 times minus 5. And the answer is again 5.